Hello, everyone, and welcome to another Directions Mag Geospatial webinar, today sponsored by our friends at Esri. I'm Barbary Duke, Managing Editor here at Directions Mag, joined by our Assistant Webinar Producer, Lynette Qualia. And if you have any questions about your connection, just drop us a note in the chat. We'll do our best to help you. We encourage you to stop by and read new feature articles, daily news, and of course, watch more webinars, always free for geospatial professionals at directionsmag.com. We are standing by to take your questions today. Type those into the question box at any time during the webinar. We'll answer as many questions as possible during our Q&A time after the presentation, and anything that we don't get to, the fine folks over at Esri will follow up with you individually. We are recording today's webinar, so keep an eye on your inbox in the coming days for that link. We appreciate your opinion on our polls and the post-webinar survey. We'll also have attendance certificates available for you as well. We are excited to have a talented team from Esri today. Hong, Julia, Mallory, and Vinay all are here to talk about some splendid examples of multidimensional analysis, and excited to show you how to get it done. So Mallory, I'll turn it over to you to get us started today.
I am Esri's Product Marketing Manager for our imagery and remote sensing products. Today, I have the privilege to introduce you to our webinar topic and our team. First off, I want to thank you everyone on the call for spending an hour with us as we discuss multidimensional analysis, trends, prediction, and change. A topic in which I think many of you will find interesting if you often face problems in which you need to understand how, why, and where things are changing. But before I get too far in, I did want to give our team of presenters a chance to introduce themselves, starting with you, Vinay.
Hi, everyone. I'm Vinay Vishwambaran. I'm a product manager on the imagery team at Esri. My focus is primarily image analysis that includes AI, multidimensional analysis, and change analysis.
Hi, everyone. I'm Julia Lenhart. I'm a product engineer on the imagery team, and I focus primarily on imagery and remote sensing applications and mostly multidimensional analysis these days.
Hi, I'm Hong Xu. I'm a principal product engineer on the same team, imagery team, and I work on multidimensional raster project.
Thank you. So let's go ahead and dive into our agenda, and that way I can let you know a little bit more about what we're going to discuss today. So since I know this topic might be new to some of you, today's discussion will go through the why behind multidimensional data. We'll talk to you more about what it is, and we'll also show you how to get started. And then we'll shift into use cases and demonstrations, so that way you can get a little bit more context for what we're talking about. And then we'll close out our discussion with a set of resources that you can utilize to continue your learning. And then, of course, we'll dive into your questions if we have time. So with that, over to you, Vinay.
All right, thank you. Now, before we dive in, I wanted to provide some context as to why multidimensional data is important, or rather why you should spend the next hour listening to us. If you're not a frequent user of multidimensional data, you may wonder how it can help you in your problem solving, right? It's become more and more vital to understand how, why, and where things are changing, not just what change has occurred. You might be interested in using historical raster data to predict flood locations, or you might be using it to model carbon stocks over time. Either which way, you're looking to find anomalies in your data sets, you're exploring trends, you're forecasting your data, or performing predictive analysis. You're also evaluating changes. So these are just some of the questions which we can answer using multidimensional data. Now, what is multidimensional data? Many of us working within the context of a GIS, you're familiar with working with two-dimensional raster data, right? Or rasters that have an X and a Y component, lat long. Some applications do require the additional dimension of height, like an elevation model. And when we're talking about multidimensional data, we're adding multiple dimensions to the data. For example, there's time, height, or depth. We could also be interested in exploring more than one variable within a multidimensional data set. So for example, temperature, sea surface temperature data, pressure. As you can see, this is a stacked data set. It's stacked as a cube of data sets or information. This is why we also refer to this data as image cubes or data cubes in certain scenarios. Good examples of multidimensional data sets include simple time series optical imagery, which can be used for simple differencing or identifying different types of land class changes. Ocean data like sea surface temperature and currents to identify trends and anomalies is a different example. Then we have weather data that's used to perform predictive analysis, and also data like soil moisture, precipitation, which will help you to drive suitable locations for growing crops of certain types. Now, all of this, we're going to show you all of these different data sets, and we show you how it's being put to use in different scenarios, different application areas. When working with multidimensional data, you need tools to also leverage those multiple dimensions and variables, and you need tools to dig deeper into your data cube. You need tools to splice through data, to anomalies, or to aggregate large volumes of data. And when I say aggregating large volumes of data, I mean something like, if you have daily stacks of imagery, you want to stack it or you want to aggregate it into weekly data, for instance. You need tools to detect harmonic trends, which can then be used to predict future changes. And you need tools to perform time series change detection. These are some of the analysis tools that we'll be going over in a bit. There's trend analysis, anomaly detection, predictive analysis, change detection. Now, all of these tools are accessible across our flagship desktop product, ArcGIS Pro. You can also access it through a thin client, through the map viewer, or you can scale your processing using image server. Now, as a developer, you can also use our APIs to automate tasks, or you can develop customized applications. Now, how do you get started with this data? As you can imagine, working with this kind of data can be rather challenging. It's a cube that contains dimensions, variables, there's a lot more. And there are different types of data sets, different types of formats. So we give you the ability to work with NetCDF, GRIB, HDF, and other formats directly as a layer within the desktop products. Mosaic datasets is a data model that is used to manage and process large volumes of imagery. We've been talking about this data model for the past decade almost. Initially, it was designed primarily for optical imagery. This Mosaic dataset is now extended to handle not just different slices of optical imagery, but you can work with multidimensional data that contains different dimensions and variables. So essentially, each slice within the dataset is efficiently managed within a Mosaic dataset. That kind of makes it a powerful way to bring together these different disparate datasets. Next, we did some work on optimizing access to these data cubes or image cubes, which needed to be pixel aligned for analysis. And the way we did it was to put together a format called CRF, cloud raster format. And that is optimized for storing imagery within the cloud. Big benefit of it is optimized for parallel writes. So it's powerful when you're writing out analytical results using distributed compute frameworks like raster analytics, as what you're going to be seeing within ArcGIS. This format can then be further optimized by transposing the data. Again, we're going to provide you with tools that will do all of these operations for you. So you can transpose the data, and this makes extraction of information across a dimension. For example, when you're generating a temporal profile, it makes it blazing fast. Now, I'll go over a few demonstrations, and this is essentially just to give you a conceptual overview of multidimensional data sets. What are they? And relevant analytical tools. So I will not be dwelling in application areas. Once I'm done with this conceptual overview of all of our tools, Julia and Hong, they'll cover specific application scenarios or application areas for these different tools and these different data types. So to start with, I'll go over a scenario where we can categorize categorical change across two images. there are these, what you're looking at here is 2 slices of the National Land Cover data set. It's accessible on the Living Atlas. It's available freely, but what we've done is we've made this available on the Living Atlas so you can consume it as services directly across multiple applications. So these are 2 different data sets, right? The land cover data set 2001, 2016. You can quickly compute change, and more specifically categorical change, because I want to see how land cover has changed between these 2 dates. And the result, the result produces a categorical change map on the fly. It shows all of the possible land cover changes between the 2 time periods. Now we can take this a step further and remap each one of these classes to visualize specific types of changes. So for example, I could look at urbanization, right? Or water loss or loss of forest. So for example, I could quickly navigate over to Lake Mead. And here we could do a quick comparison. And this kind of gives you an understanding of water loss between 2001 and 2016. Likewise, we could jump over to another location. Here's Vegas. And this is a good example of urbanization. Everything in dark red indicates the change or the increase in urbanization in 2016. Likewise, we have a series of different locations. I've bookmarked a bunch of different locations. For example, Phoenix is another example. Turning this on and off, the regions in dark red indicate urbanization over 15 years. Right now, moving from 2 images, let's take it up a notch and move to a multidimensional data set. This contains multiple variables and the dimension of depth and time. To start with, we could just pull in, this is a netcdf data. We can just pull in the data set directly into the desktop application using our map add option. You can add rasters directly, and it's pretty straightforward. You go and add, just like how you add any other data to your GIS, pick your image, your raster. In this case, specify the variables that you're interested in. In this case, I'm interested in seawater salinity, seawater temperature, and I can add it as a multivariate data set. Now, the benefit of adding it as a multivariate data set, it's added as a container, right? This is a container which contains multiple variables which I can slice and dice through, and I can step through time, look at any given time period of my data set, and I have another dimension of depth, right? So I could quickly explore a dimension of depth. We could step through time and visualize changes as well. So this is a very simple example. You could see within a matter of 3 clicks, I could slice and dice my data set, pick a specific variable, a time period, and a specific depth that I'd like to work with my data. This is just visualizing of the data. Next is, again, visualization. Another example. This is a pretty cool and intuitive way to explore this data. So you're looking at the ecological marine unit data. The data goes beyond the surface in this case, and I jump to a location and you know what I mean. This data we can easily explore with the appearance tab. Here I can apply a vertical exaggeration if needed. And similar to the previous data set, this data set contains a boatload of variables that I can explore. Then you can change the brightness on your data set. You can control it subtly as well if needed. Or, I could switch quickly, just jump to the symbology of the data set. And here I can pick values that are of specific interest to me, right? Once we have this, we can also change transparency in a very controlled manner. You can add on multiple control points and change the transparency of your layer. And it's not just this. Once I've extracted this layer, you can create ISO surfaces. Here's an ISO surface that I've created, right? And you can do the same thing here as well. Slice and dice your data. You can pick a certain value that you want to work with. And you can section your data as well. So you can change the position that you want to work with. So again, this is quick visualization of your data. We have a series of tools that will enable you to work with this data as well. I'm not going to dive into the details of that, but I just wanted to show you how you can visualize, you can slice and dice different dimensions and different variables that exist within a multidimensional data set. I'll dive into a couple more demonstrations now, just to show you the kind of analysis that we can do. Again, this is not application specific. This is just to give you a conceptual overview of the tools that we have. So this is the sea surface temperature data. This is 35 years of monthly observations of data. Now, here you can see I've got a complete stack of imagery. That's approximately 400 slices of imagery. Using our tools, our aggregation tools, for instance, I could aggregate my weekly data into annual slices. So these 400 slices, I pulled it down to 35 slices. Many a time you don't need that dense a data set depending on the analysis that you're doing, right? So hence I pulled it from 400 slices down to 35 slices of imagery. Next, I've generated an anomaly data set. We have tools to enable you to do that. So I'm looking for anomalies within my data set. Step through time, and you can see patterns, increase in temperatures or decrease in temperatures, essentially different kinds of anomalies over different time periods. And based on those anomalies that we just noticed, we could quickly create a temporal profile for any given region within my map. So I'm using my data set, pick a point. There are outliers, which we can see here. And if you look at this, this is essentially the change in sea surface temperature over time. You'll see two outliers. One is 1983, and the next is 1998. Those are 97, 98 time frame. Those are essentially, as you all are aware of, this is essentially the El Nino years. So easily, I could easily visualize my data set, perform real simple analysis, and visualize certain phenomena. Lastly, one of the set of tools that I want to show you is the trend and predictive analysis tools that we have. Again, this is used for effective analysis of multidimensional data. You're looking at yearly precipitation data and using our trend analysis tool. And in this case, my objective is to, let me pull that up. In this case, my objective is to predict future precipitation, so I can use it for doing things such as suitability analysis and predicting where to grow certain types of crops. Once I run the tool, the result is a trend data set, and the purple regions are indicating increasing precipitation trends, and the green areas indicate decreasing precipitation trends. This data set can be used to predict future precipitation. And this is what my result looks like. In the interest of time, I'm not running any of the tools. And I've predicted my data all the way out to 2028. And like I said, this can now be used in applications such as suitability analysis. You can predict where to grow certain types of crops. And Hong will be showing you quite a few interesting examples of how this is put to use in several application areas. Now, with that conceptual overview of all our tools, I'll hand it over to Julia, who will go into specific applications and examples. Julia?
Great, thanks, Vinay. Thank you. So Vinay just showed you all a bunch of examples of how you can perform these types of analyses. I'm just going to show you a few more examples and application uses for change detection and analysis for your GIS work. And we're going to start with urban development. So we're going to take a look at how we can find out how the urban landscape is changing in a few different regions over time, and we'll use some satellite imagery. We're going to take a look at a few different examples here. So we're going to start with Happy Valley, which is a suburb of Portland, Oregon. And now we're interested in seeing how this area has changed in terms of vegetation cover. So Happy Valley is one of the fastest growing areas in Oregon. Maybe it is the proximity to Portland or the very chipper town name, I don't know, but we wanted to know just how much population is impacting vegetation in this area. So we took 2 high-resolution images collected by and provided by Planet, one in the summer of 2017 and one in the summer of 2020, and here we're looking at 2020. And we calculated a vegetation index called the Soil Adjusted Vegetation Index, or SAVI, for each of these images. And so here's the one for 2017, and I'll turn on the one for 2020, and you can see that some of the data changes here. So when Vinay showed you an example of change computation between 2 images, we performed a categorical difference. And I'm going to use the same function, but this time I'm going to calculate the relative pixel value difference between these 2 images. And I'll go ahead and create that layer. And lightning fast, we get this new output. In this case, purple indicates that there are increases in vegetation, where green is indicating a decrease in vegetation. I'm just going to quickly invert that so it's a little bit more understandable. So now we're seeing that in green we have higher vegetation and in purple we have lower, and so we're seeing these like massive areas that have lost vegetation. And if we zoom in, and I'll just turn off these other savvy layers, I can use my swipe tool and see what's going on underneath this, and I can see that in fact these are what looks like big new developments, especially this one here where my mouse is currently. It looks like a new housing development. Down here we have this large area that's been cleared, probably for even more development. Right, and from here we can classify this data, we can quantify it, we can use it in other models. And again, this is just another simple example between 2 images. Now let's take a look at a more complex example where we're going to use a time series of images collected from a satellite to see how things have changed over time. So here you're looking at Massachusetts, which is where I'm from, and I've seen quite a lot of change over the last 20 years in this area, but we were interested in exactly how land cover has changed for this area over time. So we used a stack of freely available Landsat images, 286 images collected around every 15 days from 2002 all the way to March of 2020. Now, to categorize imagery into land cover types, we have to train the software to recognize each land cover type that we're interested in. So for example, we have to tell the software that when it's seeing this blue area where my mouse is, that's water, and we need to train it that, you know, maybe in this area over here, we're looking at forest. Now in the past, you could do this type of classification for one image at a time and then compare across images. But now we're able to train and classify this entire stack of images all in one go. So I can open up the training sample manager here. And here are the different categories that by default I have access to. And I can just start training my software and telling it, you know, hey, this area that I've drawn here is water. Now, because I'm looking at the Bay Area, it's very unlikely that this land cover type has changed much between the years. So I can select this polygon, change the slice that I'm looking at to verify. Maybe let's look at back where we started in 2002. And you can see that obviously this has not changed much from water. So I can simply duplicate this training sample. And as you can see, the training sample has collected not only the fact that this is water and the spatial information I gave it, but it also has some timestamps. And so I can continue to do this for each of the categories that I'm interested in. And when I'm done, I have a group of training samples available that have time information and land cover category information, right? And so I can feed all of this information into a training tool, like the train random trees classifier here. I tell it which value is my time field, and I go ahead and run that to train the sample, and this would just take about 30 seconds to run. I can then enter all of this information into my classify raster tool and produce an output that is a cloud raster format file, a multidimensional file. And the result is a stack of land cover maps, one for every single slice in my input data set. So I can compare directly between 2002 and 2020. I can compare between every single slice and see how things are changing over time. Now I went ahead and I extracted the very first land cover map from this series and the very last one. And I ran the compute change function again using the categorical change that you saw in Vinay's demo. And here again, we see every possible land cover transition. And I'll go ahead and highlight one of them, for example. So in red areas, we see things that changed from forest to barren. So I'll go ahead and zoom in on one of these areas. So we're seeing these big chunks that changed from forest to barren area. And I went ahead and created a temporal profile for one of these clustered regions. And here we can see that for an area of interest on my map, I can find out exactly when a pixel changed from forest, which in this case was in 2004, to barren in 2005, and then stayed barren for a few timestamps, and finally was converted to developed in 2006. So this is a great way to find out not only where something changed, but also exactly how it was transitioned and exactly when that occurred. Now, another great example of how to use time series change analysis is forest disturbance detection. So we were interested in finding out where and when forest disturbances occurred in Yosemite National Park. So we used around 270 Landsat images, and we ran a new tool that extracts the date at which there were abrupt changes in land cover. And this also accounts for seasonal and long-term gradual trends. So it's only pulling out those changes that happened very abruptly, that are usually indications of intentional or unintentional land cover change, right? And we identified a cluster of pixels that indicated a large area in Yosemite that experienced this abrupt change all at around the same time in 2018. And if you're from California or you follow our wildfires, you'll know that in 2018, there was the Ferguson fire in Yosemite that impacted this area. So we were able to extract the burn scar of a fire using these tools. Sorry. Another great example is the use of time series change analysis in natural resource assessment. So we wanted to find out how the area used for surface coal mining in Appalachia in the eastern United States has changed over time. So we used a large collection of Landsat images, again, collected from 1985 until 2018. And we created a custom workflow using Python that allowed us to set certain thresholds so that we could find out exactly how much area was being used for surface coal mining. And you don't have to read through all of this, but I just wanted to show that we started with this stack of Landsat data. We performed a vegetation index. We were coded in some thresholding that was a good indication of where surface coal mining was happening based on several research papers, and we categorized that. And the final outcome was this changing map of how surface area has been used for land cover, for surface coal mining over time. And we classified this and were able to extract area information to find out that between 2005 and 2010, there was a peak in the land that was used for this type of application. And it has since dwindled, but has gone up in the last year. And I'd be interested to see how it has been the last 2 years or so. So that's it from me. I'm going to hand it off to Mallory.
Thank you. That was really great, Julia. So far through Vinay's introductory demos and Julia's land cover examples, we demonstrated analyzing change across 2 images as well as a collection. So we'd like to hear from you. What kind of change analysis do you perform the most? Do you do that across 2 images, or do you do that across a collection of time series images?
And we have a nice little competition going here. It's going back and forth. So folks, get those votes in quickly and we'll see if we have a winner. All right. So let's share those results. And it looks like I inched away at almost a tie.
Yeah, almost. But yes, clear winner there. But thank you so much for answering. So with that, I'll pass it over to you, Hong, to continue on.
Thank you, Mallory. I'm now going to show some use cases for using trend and predictive analysis tools that Vinay talked about earlier. Research has suggested that nightlight can be used as a proxy to population, economic growth, and urbanization. I'm going to use nightlight data and the multidimensional tools to model the urbanization patterns in the global scale. So this is the nightlight data starting from 1992 to 2013. It is yearly across 22 years. And let's zoom in. And this is the nightlight data over Asia. Let's turn on the boundary. So this is the nightlight data in 1992. Oh, sorry, I have an accident here. I'm sorry, apologize. So this is the 1992 nightlight data over Asia. And then let's switch to the year of 2013, and we see a big change. So to analyze the trend and model the trend, I use generate trend raster, and it would take about 6 minutes and generate an output. And I display with RGB, where the red band has a positive slope, which means the increase in nightlight, and the green band has a negative slope, which means a decrease in nightlight. And the green is the intercept of the model. So green means no change. The dominant color around the cities in China or in India, this indicates a growing trend of population and urban expansion. And let's move to the other part of the world, which is the US, and we see the trends vary spatially. Let's turn off this. The big red spot over the up in the north, this is the North Dakota oil boom start in the 2007, around 2007, which caused a big increase of the nightlight. And those green spots that are surrounded by the red pixels, this indicates the urban expansion. So we know that in Texas or many cities like in Texas and Arizona, many companies have moved to these cities, which caused the urban to grow. So this is an example of using multidimensional tools to look at the urbanization pattern. The same analysis can be done using Python as well, Python notebook. So here we import the library and we open the input data, which is the multidimensional raster. And then this is the first slice of the image. And then we run the generated trend raster and the display using RGB. So this is the very nice trend model. It shows the global, the urbanization in the global scale. So this is the first demo. So multidimensional tools can also be used in conservation to explore how climate change can affect the ecosystem. Sea surface temperature are rising due to climate change with unknown impacts on many ecosystems. We're going to predict the future sea surface temperature out to 2030 and explore how that can affect the marine species. For analysis, I use an image cube that has 2,000 weekly slices of the sea surface temperature, which are collected over the past 35 years. And the first step is to generate a trend using the trend analysis tool. And from the tab, we can use the trend analysis tool to generate a trend raster. And here is the result. It's showing increasing temperature trends in the red areas on the map. The next step is to take this data and input it into the prediction function and create a function layer on the fly. So the result is a global prediction map of monthly sea surface temperature generated on the fly. And the data set is projected out to 2030. This is we can create a temporal profile of the predicted data set to explore regions and ecosystems that will be affected by future temperature increases. For example, the harmonic or cyclical curve shows the seasonal patterns of the Pacific coast of Mexico. The line is the yearly trend, which shows that this area is predicted to increase in the temperature. We can take this predictive analysis a step further, and with a series of geoprocessing tools, we can create a time series risk map to visualize areas that are experiencing prolonged heat stress. The risk map shows risks all the way to 2030. So this is May 2023, and this is September 2023. And you can see here in the Gulf of Mexico, extended periods of prolonged heat stress in July of 2028, which can intensify weather activity and affect marine life in the region. Or on the coastal triangle in August of 2028, where heat stress can lead to bleaching of coral reefs. So the application of this type of predictive analysis is endless. Another use case on conservation side is deforestation. As we know that deforestation will affect our ecosystem, weather patterns, wildlife, and so on. So we want to understand where deforestation has occurred and is likely to occur in the future. So we use MODIS NDVI dataset from 2001 to 2019. We aggregated into monthly maximum NDVI and then generate this trend map. The green pixels have a negative slope, meaning decreasing in the maximum NDVI, and the purple has positive slope, meaning increasing. We found that vegetation decreases in large areas in South Africa and increases in other countries such as India and China and some European countries. Public health is another area where multidimensional analysis can be applied. As we know, particulate matter, PM2.5, is an important indicator of air quality. And we want to find out the regions where PM2.5 level exceeds WHO, World Health Organization guidelines. We used PM2.5 data created from NASA Social Economic Data and Application Center, which is the yearly average from 1998 to 2016. We generate a few analysis datasets using the multidimensional tools. The first dataset, this is the maximum PM2.5 map over 19 years. The WHO guideline for health is to keep PM2.5 under yearly average of 10 microgram per cubic meter. But we see that many regions exceeded this guideline in the 19 years. The second dataset analysis map is a trend map. It shows the distribution of PM2.5 trend, where we found that the decreasing trend in the South US and some European countries is shown as green color, and the increasing trend, PM2.5 trend, in Asia and Africa, shown as the dark purple color. The third dataset is the frequency map. In red, we see regions that most frequently exceeded the WHO guideline, and the blue means less years exceeded the guideline. So this provides both the spatial and the temporal views of PM2.5 distribution. This map was generated using RAS function combination of RAS functions and also the aggregate tool. As we know that air pollution has been dramatically reduced globally since the start of COVID-19, so we just hope that it will last even after COVID-19 is over. The last example I'm going to show is the application in agriculture. The rising temperature causes changes to crop conditions. GDD, growing degree days, a measure of total amount of heat accumulated using during a growing season. This has been used as an indicator of plant growth. Grape is one of the major crops in California, so we want to understand how the changing temperature will affect grape and wine production. We use two temperature variables from DMAT datasets, daily minimum and daily maximum temperatures over 35 years. And we created this yearly growing degree GDD time series, growing degree days. And we can see the dramatic increases in the temporal profiles at the two locations in California. And we took a step further and created the yearly suitability map for grapes based on the calculated GDD. And we found that the suitability regions of different grapes vary dynamically from year to year. It shows that the changing temperature and the changing growing degree day will affect grape and wine production greatly. So this concluded my demos, and now I'm going to pass to Mallory.
Hi again. So we do want to hear from you again on another poll. So much of what you've seen so far in regards to analysis has been done in our desktop application, ArcGIS Pro, but we'd like to know from you, which client applications do you normally use when processing and analyzing your data? Desktop applications, web clients, notebooks, or other developer animation environments, or automation environments, I apologize.
I have a very solid winner for this. Not that that's terribly surprising. So let's get this shared, and 86% are using their desktops.
Yeah, that makes sense. That makes sense.
Yeah.
Thank you, everyone. So back over to you, Vinay.
So those were a fantastic set of examples we covered today. There was prediction, there was change, trends, Now, there are many more cases which we obviously couldn't cover today because of the time restrictions. Now, this slide, it just lists some of the other scenarios that we worked on. On the top left, using NASA's atmospheric science data, we're able to predict worldwide energy resources. That's another example. Multidimensional winds data set can be used to predict future weather phenomena using the predictive analysis tools that we showed today. A multidimensional data set with temperature and precipitation, soil moisture, that can be used in agricultural applications such as determining suitable locations, time periods to grow specific crop types. And here on the third on the third diagram or the third figure, you can see an example of how changes in temperature affects coffee growing regions in Europe. You can also see multidimensional analysis tools. You can see how it's being used to evaluate sea ice concentration and how it's changing within the Arctic. We use data from the National Snow and Ice Data Center to map the trend in sea ice concentration over the past 30 years and found that trends and anomalies, they widely vary depending on location, but that overall most locations within the Arctic are experiencing sea ice loss over time. The next line on the right here, we have plant hardiness zones. This informs farmers and gardeners on the types of fruits, types of vegetables that can be grown in a given climate. We use trend analysis, predictive analysis tools to predict temperature in the future to see how distribution of plant hardiness zones in California can really change as a result of climate change. Another good example, and this is in line with something Hong has already shown, is environmental regulation assessment. In California, a lot of efforts have gone into reducing the amount of harmful pollution in the air we breathe. We took data collected at stations throughout the state to create a data set containing 20 years of particulate matter concentration data. And then we performed a trend analysis to highlight impact of environmental regulation. Forest services, they can use the tools you saw today to create products, deliver information on the status and trends of forest resources. You can create and update maps showing forest carbon, above ground biomass, or maps of tree species. That is then used to support scenario planning, wildfire fighting, and similar situations. And lastly, on the bottom right, that's a categorical change map that is generated using time series planet imagery, and that essentially indicates urbanization. Now, a lot of the data you saw today is available on the ArcGIS Living Atlas. All you need is an ArcGIS online account, and you can access these data sets as image services, which you can consume directly within your desktop applications. You can write applications against that, web applications against that, consume within map services. Then you can consume them as story maps. Even this is accessible through the Living Atlas. And then we have a host of web applications as well. I'd encourage you all to try out these services and applications and explore what you can really do with our technology, what you could do with all of the tools that we've shown you today. And with that, I'll hand it back to Mallory, who's going to close this out for us.
Thank you, Vinay. Yeah, so I know we had some questions come through in regards to resources. So I did want to share a handful of them that might be of value to you. So the first three are really resources to get you hands-on. So we have a learn lesson there that goes over coral bleaching. We also have a tutorial that you can walk through. And for those that are interested in online learning, we do have a MOOC. Although the title is Spatial Data Science, the New Frontier into Analytics, we do cover rasters in there. So that might be of interest to you. Just a heads up, it is a 6-week course, and it is running from October 28th through December 9th on that. For those interested in doing a little bit more reading, we do have a blog on calculating change. This one is an interesting one because it does walk you through step by step on how we went about understanding water loss in the desert. And then those that are wanting to engage with us a little bit more, we do have a community, our GeoNet community, that's all about imagery and remote sensing. So we encourage you to check that out as well. So with that, I do want to launch our last poll. And this is really for those that are interested in gathering a little bit more on this topic and wanting to talk with one of us. So if you are interested in speaking to an Esri subject matter expert, do let us know. If not, that's fine. But we do hope that the resources that we provide, which we will put up back onto the screen, will help get you through to continue your learning on this topic. So we'll just leave that up for a little bit longer. As that is up, I do want to transition to some of the questions that we do have, if that's okay. The first one, Julia or Vinay, question is, I want to see soil erosion and land loss due to river flood over time. Can I use land cover data from the Living Atlas to see that change?
Yeah, sure. Go ahead.
Okay. Yeah, this is Julia. It depends. So the NLCD data that Vinay showed in his demo is 30-meter resolution. So if it is change that would be visible at that resolution, then absolutely. If it happened in the time period, right? So NLCD data has, and the National Land Cover Database is available for multiple years, and it's available at 30-meter resolution. So any change that has happened within the time span that they have provided and that can be visible at 30 meters or greater will be visible from that data set. So it depends on what you're looking for. And there's also soil data available on the Living Atlas as well. So you could take a look at that.
And also to add to what Julia said, a lot of the analysis right now that you can do is mostly visualization. But what we're doing is we're extending ArcGIS Online to provide you with direct access so that you can work with the complete data set and perform analysis against the complete data set. So using our on-the-fly processing and on-the-fly raster function capabilities, you can visualize and perform the different kinds of analysis. But if you want to do large-scale analysis, we're working on that currently.
Thank you. So our second question to Julia, and this is in reference to your land cover example. You were making samples of land cover over time and you showed change, but how sure are you that this change is significant, i.e. making a change in land cover and not partial change?
That's a great question. And I will just say broadly that as with any analysis, you want to do some double checking, right? When you create an analysis output, often with GIS and especially with image classification, we want to make sure we're considering the accuracy of our output, whether that's just by visually looking at the imagery for the dates that you're interested in to verify that the classification shows the correct results, or if you actually physically go to that place on the ground to verify that what you're looking at is right. So in this case, I did the temporal profile that we showed. I did double check to make sure that the imagery shows, in fact, the timestamps were correct and that the conversion is correct. However, you know, it's always best to double check, and I just wanted to make sure that we talked about that specifically as in reference to just making sure you're checking the accuracy.
Great. So our third question, and this one I think is appropriate for you, Vinay. Where and how can stacks of Landsat data or Sentinel data be downloaded?
So if you check out, I mean, literally, if you Google Landsat data sets, or you can check out, there's the Sentinel Hub, which provides you with access to the Sentinel data. The Landsat Look data is available. If you search for Landsat Look, you can get access to all of the Landsat data, and it's accessible through an FTP site. There is a download website as well for its, and it's just slipping my mind right now. Hong or Julia, what's the website where we downloaded the USGS provides access to all of this data, but there's a specific site.
The Earth Explorer.
Earth Explorer, that's the one. So you can download all of the data using the Earth Explorer as well. They give you a command line option, making it really simple to download all of the data. And lastly, as part of, so we have a website, it's called the Imagery Workflows website. If you head over to the image management section, there's a portion over there which will show you how to set of scripts which will let you download Sentinel and Landsat data directly, and it will enable you to create your own Mosaic data set locally. So it'll go through the complete process and automate the process to download the data for you to your local machine or on the cloud store and create relevant Mosaic data sets which you can use for analytical purposes.
Great, thank you. I think I'll need to add that as a resource. For our fourth question to Hong, how do you deal with cloud cover for stacks?
Thank you. Yeah, that's a very good question, and it's a very critical step for when you work with the time series data, analyze using time series data. And what we recommend that you, because when you download the data from Earth Explorer, there is a ARD data set, analysis ready data. So we recommend you use that because the ARD data comes with cloud cover. So you can use the quality band cloud cover to mask out the cloud. So use RAS function. We can use RAS function to mask out the cloud.
Actually, I think that's a great segue into one of our other questions that we got. And Julia or Hong, maybe you can answer this one. Were most of these analyses using GP tools or raster functions? Where do you draw the line between choosing a GP tool or a raster function?
Okay, I can answer. Yes, so multidimensional raster can be used in both GP tool and a RAS function. But there are basically two types of multidimensional raster. Sometimes you analyze, you have a time series data, but then you want to compute across the dimension. So in this case, if there are, the dimension, number of dimension values across too large, like, exceed like hundreds and 1,000, and maybe that is a good time to use the GP tool, because GP tool create an output. Function is performed on the fly. Sometimes if you work with multiple variables, each like 2 variables, but then you compute based on the same time. For example, the GDD example, the GRIP example that I used 2 variables, minimum temperature and maximum temperature. I need to compute and do computation between the time. So in this case, I can use RAS function.
And just to quickly add to that, raster functions is blazing fast. It's on-the-fly visualization. So it's not necessarily an analytical product. The big benefit, you can try out different parameters and keep changing the results of your visualization. Once you're happy with the parameters, you can either deploy it as a geoprocessing tool and write out the raster data set to disk.
Yeah, we're out of time. So many great questions. So folks, if you do have some very final thoughts, go ahead and type those in, and we'll be sure and share those with our talented team here over at Esri. So thanks again for attending today. We hope that you will keep an eye on your inbox. We'll be in touch with the archived recording so you can view everything again. We'll also have all these links that you see here on the screen, and maybe Mallory can dig up a couple more resources for us as well. We appreciate you completing our brief survey on the way out. Special thanks to Julia, Hong, Mallory, and Vinay for sharing their talents and all the cool maps. And we hope everyone has a great day. Tells a friend about Esri and Directions Magazine. Thanks, everybody. Have a good day.